So we're looking at, I forgot to record, I'm sorry, it's the last 10 minutes of class. But we're looking at problems from the parameterized curve handout. We were doing these problems. We verified that these were parallel. Sorry for you on Zoom, I'm just recapping in case anybody wants to watch this later. So we verified these are parallel just because the direction vectors are parallel. We did pick a point on L2 and it was on L3, so the two lines are actually the same line. 19 and 20, it might be on the board. Actually, yeah, let me switch the boards again. So you can pause the video if you're watching this later. This was sort of what was going on. In 19 and 20, like we just pause and look at this. So right, you saw 19 is asking if the two particles intersect, so same time, the time would be the t would be the same in that case. And if you try to solve this, it doesn't work. Three equations, one unknown. The paths would intersect if you know, basically if the x's, y's, and z's ever match each other in these equations. So I just set them equal to each other with a different parameter. And if you solve these, you actually get values and you get a point. Sorry, I'm talking for posterity because I forgot to record. I'm talking to myself. Like I forgot to record. So I'm just going through this quickly. If anybody wants to watch this later. Yeah. And then 21 was easier than it looked about intersecting the line with the plane. Because you just literally plug the line equations into the plane to intersect them, and you find the point of intersection. Okay. So now to 22. So did people figure out the thing with 22? What did you figure out?
1 over 2.
But how did you figure it? Yeah, like what was your insight?
So it's like this formula is basically the normal vector, and we parameterize it.
So it's a specific line, but it has to go through what? The origin. Yeah. Oh, I just erased the equations for the line. Oops. Oh well. Yeah, if you have some plane in space, you want the point closest. So just because we're running low on time, 22 about the line, this point on the plane closest to the origin problem we've solved in multiple ways, because we could also solve it. You're minimizing x squared plus y squared plus z squared, and you could eliminate a variable and solve it as a optimization problem for a function of two variables. You could use Lagrange multipliers, minimize x squared plus y squared plus z squared with respect to the constraint. Or you could do this where you basically, it looks like the insight most people had was that this point is sort of like, it's sort of like the line from the origin to the plane is perpendicular. That's like the closest point. So if you parameterize this line, parameterizing this line and then just intersect line with plane like you did in the previous problem, you get the answer, right? So this line is through the origin in the direction. What was the plane? Same plane? 2, 1, 2i plus j plus, wait, 7? No, 3. 3k. So basically you get this line, right? And then you plug these into the plane equation. And you found to 2x plus y plus 3z equals 7. I think you get t equals a half. Is that what somebody told me? And so you get the point 1, 1/2, 3/2. You could check this with Lagrange multipliers and with optimization and see if you get the same answer each of 3 different ways. Okay. And then the point on L2 closest to the origin, I saw some different groups do this nicely, which is basically you're trying to minimize x squared plus y squared plus z squared, but x, y, and z are all functions of t. Yeah, it's funny. It's a different. There's this one's all about the one about the point on the plane close to the origin is all about geometry. The one about the point on the line close to the origin is really just a single variable calculus problem, right? Because we have, oh, I erased the equations now, but we have, what was it? So you want to minimize, this is 23. Minimize x squared plus y squared plus z squared. And what are the, but what were the equations for line for L2 again? I guess they're on it. Yeah, so if you plug those in, you get a function of one variable. And it's single variable calculus. So you get a single variable calculus problem that you can solve. You have a function, basically the distance, because if you think about it, yeah, the line is a one-dimensional object. So the distance from a point on the line to the origin should be able to be given as a function of just t, right? As a function of one variable. So this will calculate the square of the distance from any point on the line to the origin. And so then you're just trying to minimize that. Did it work out? Did people get answers? Was t equal to 0? No? I mean, you got to differentiate this, set the derivative of this equal to 0. I guess there's some chain rule stuff. T equals -2. And then what point? 2. And so you get the point 0 to -2. Is that the point other people got? Anyways, it's just math from that point, but yeah, good. Yeah, you have to differentiate, set this equal to 0, solve for t, which I guess you can use. You can FOIL it out or you can use chain rule. Good. Okay, so now I just kind of like this section because you solve all these problems. The thing that we're going to do Friday and then going into next week is we'll start talking about what it means, what these other type of integrals called line integrals. And so you actually, it's gonna involve paths, parameterized paths, and also vector fields. So I'll talk about vector fields a little bit, and then I'll try to introduce line integrals a little bit before the break. Then we can do it seriously after the break. All right, thank you all. I'm also gonna send an email. I have a plan for after break, rest of the semester. It involves an optional final exam. That's a good thing, I think. But I'll email you guys the next day or two about that. All right. Well, it involves a required second midterm after the break, but then an optional final. Yeah. Yeah, basically. Yeah, like I mean,